Good evening and welcome to the session number 26 from the chapter of electric charges and fields. The topic is the calculation of work done in rotating an electric dipole when placed in an external electric field. So before proceeding with some of the numerical problems from the topic of electric dipole, I thought it important to first of all discuss this point of the calculation of work done in rotating an electric dipole when it is placed in an external electric field. So from the session number 27 onwards, we will be solving few important numerical questions from the topic of electric dipole. So here there is one dipole AB which is placed in a uniform external electric field, say E. That is, the intensity of the electric field is equal to capital E, and this dipole is the angle between the dipole moment and the direction of the electric field is theta 1. Here dipole moment P is equal to 2A into Q. In the session number 24, we have learned that the dipole moment is equal to the separation between the two charges of the dipole multiplied by the magnitude of any one of the charge. So in this case, the dipole moment will be equal to 2A into Q, and the direction of the dipole moment is from the negative charge towards the positive charge. So theta 1 is what? It is the angle between the direction of the dipole moment and the direction of the electrical field. So in the session number 24 also, we have also learned that the torque acting on the dipole is given by PE sine theta, where theta is the angle between the direction of the electric field and the dipole moment. So in this case, if the dipole is placed at an angle of theta 1, that is, if the angle between the direction of the electric field and the dipole moment is theta 1, then the torque acting on the dipole AB will be equal to PE sine theta 1. Now, if I rotate this dipole from theta 1 to theta 2, as shown in this figure, that is, if I will rotate this dipole AB from theta 1 to theta 2, then the new position of the dipole will be CD. So in this case, some amount of work will be done. And we know that in rotating a body through a very small angular displacement, say d theta, the work done is equal to torque multiplied by d theta, where d theta is the angular displacement. So if I integrate this equation, so here what I have done is I have simply substituted the value of torque, that is P is sine theta, in this equation. So I have finally got this equation. I have denoted this equation as equation number 1. So dW will be equal to PE sine theta d theta. Now in order to calculate the total amount of work done in rotating this dipole from theta 1 to theta 2, what I will do is I will simply integrate this equation within the limits of theta 1 and theta 2. This equation, this dW is equal to PE sine theta d theta, is the work done in rotating a dipole through a very small angular displacement, say d theta. So in order to get the total work done in rotating a dipole from theta 1 to theta 2, I will simply integrate this equation within the limits of theta 1 and theta 2. So this is finally, let us say this is the equation number 2. So the integration of dW, this is equal to the integration within the limits of theta 1 and theta 2, PE sine theta d theta. Now P is the dipole moment and E is the intensity of the electric field. Both these two values are constant. So finally I will be getting the total work done equal to PE, and integration of sine theta will be equal to minus cos theta, and the limits are from theta 1 to theta 2. So finally the total work done is equal to PE in bracket cos theta 1 minus cos theta 2. So in the session number 27 and or you can say in the forthcoming sessions, I will be now taking up the questions from the topic of electric dipole, and the questions which I will be taking up will pertain to the topic of or you can say from the topic of this torque which is acting on an electric dipole, the work done in rotating an electric dipole when it is placed in an electrical field, and on the dipole moment. So till then, have a nice day. Bye.